Welcome to NUM Academy CET Coaching Classes 2020. Subject Chemistry. Topic Some Basic Concepts of Chemistry from First View. Synopsis. Properties of matter and their measurement. Physical properties are those properties which can be measured or observed without changing the identity or the composition of the substance. Example: color, odor, melting point, boiling point, density, etc. The measurement or observation of chemical properties requires a chemical change to occur. Example: burning of magnesium ribbon in air. Chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Quantity, unit and its symbol. Length, its unit is meter, symbol is m. Mass, unit is kilogram, symbol is kg. Time, unit is second, symbol is s. Temperature, unit is Kelvin, symbol is K. Amount of substance, unit is mole, symbol is mol. Electric current, unit is ampere, symbol is A. Luminous intensity, unit is candela, symbol is Cd. Prefixes in SI system. Multiple, prefix, symbol. 10 power minus 12, prefix is pico, symbol is P. 10 power minus 9, prefix nano, symbol N. 10 power minus 6, prefix micro, symbol mu. 10 power minus 3, prefix milli, symbol M. 10 power minus 2, prefix centi, symbol C. 10 power minus 1, prefix deci, symbol D. 10 power 1, prefix deca, symbol Da. 10 power 2, prefix hecta, symbol H. 10 power 3, prefix kilo, symbol K. 10 power 6, prefix mega, symbol capital M. 10 power 9, prefix giga, symbol capital G. 10 power 12, prefix tera, symbol capital T. Important things to know. Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. Volume. Volume has the units of length cube. So, volume has units of meter cube or centimeter cube or decimeter cube. A common unit is liter. It is not SI unit. It is used for measurement of volume of liquids. 1 liter is equals to 1000 ml. 1 centimeter cube is equal to 1 decimeter cube. Third, temperature. There are 3 common scales of temperature to measure. First one, degree Celsius scale, degree Fahrenheit scale, Kelvin scale. Here, K is the SI unit. K is equal to degree Celsius plus 273.15. There are some quantities to be defined. First one, mass percent. It is the mass of the solute in grams per 100 grams of the solution. Mass percent of the solute is equal to mass of the solute divided by mass of the solution into 100. A 5% solution of sodium chloride means that 5 gram of NaCl is present in 100 gram of the solution. Second, volume percent. It is the number of units of volume of the solute per 100 units of the volume of solution. Volume percent of the solute is equal to volume of the solute divided by volume of the solution into 100. A 5% volume by volume solution of ethyl alcohol contains 5 cm cube of alcohol in 100 cm cube of the solution. Third, molarity. Molarity of the solution is defined as the number of moles of the solute dissolved per liter or decimeter cube of the solution. It is denoted by the symbol capital M. Measurements in molarity can change with a change in temperature because solutions expand or contract accordingly. Molarity of the solution is equal to number of moles of the solute divided by volume of the solution in liter is equal to N by V. The molarity of the solution can also be expressed in terms of mass and molar mass. Molarity of the solution in terms of mass and molar mass is equal to mass of the solute divided by molar mass of the solute into volume of the solution in liter. Molarity equation. To calculate the volume of a definite solution required to prepare solution of other molarity, the following equation is used. M1V1 is equal to M2V2, where M1 is equal to initial molarity, M2 is equal to molarity of the new solution, V1 is equal to initial volume, V2 is equal to volume of the new solution. Fourth, molality. Molality is defined as the number of moles of solute dissolved per 1000 gram or 1 kg of solvent. Molality is expressed as small m. Molality is equal to moles of the solute divided by weight of solvent in gram into 1000. Fifth, mole fraction. It is the ratio of the number of moles of one component to the total number of moles, that is solute and solvents present in the solution. It is expressed as X. Mole fraction of solute is equal to moles of solute divided by moles of solute plus moles of solvent. Mole fraction of the solvent is equal to moles of solvent divided by moles of solute plus moles of solvent. Mole fraction of solute plus mole fraction of solvent is equal to 1. Scientific notation, in which any number can be represented in the form capital N into 10 power small n, where small n is an exponent having positive or negative values and capital N can vary between 1 to 10. Example, we can write 232.508 as 2.32508 into 10 power 2 in scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 power minus 4. Precision. It refers to the closeness of various measurements for the same quantity. Accuracy. It is the agreement of a particular value to the true value of the result. Significant figures. The reliability of a measurement is indicated by the number of digits used to represent it. It expresses it more accurately. We express it with digits that are known with certainty. These are called as significant figures. They contain all the certain digits plus one doubtful digit in a number. Rules for determining the number of significant figures. First one, all non-zero digits are significant. For example, 6.9 has 2 significant figures, while 2.16 has 3 significant figures. The decimal place does not determine the number of significant figures. Second, a zero becomes significant in case it comes in between non-zero numbers. For example, 2.003 has 4 significant figures. 4.02 has 3 significant figures. Third, zeros at the beginning of a number are not significant. For example, 0.002 has 1 significant figure, while 0.0045 has 2 significant figures. Fourth point, all zeros placed to the right of a number are significant. For example, 16.0 has 3 significant figures, while 16.00 has 4 significant figures. Zeros at the end of a number without decimal point are ambiguous. Fifth point, in exponential notations, the numerical portion represents the number of significant figures. For example, 0.00045 is expressed as 4.5 into 10 power minus 4 in terms of scientific notation. The number of significant figures in this number is 2. While in Avogadro's number, that is 6.023 into 10 power 23, it is 4. The sixth point, the decimal point does not count towards the number of significant figures. For example, the number 345601 has 6 significant figures but can be written in different ways as 345.601 or 0.34561 or 3.45601, all having same number of significant figures. Retention of significant figures. Rounding off figures. Rounding off procedure is applied to retain the required number of significant figures. First one, if the digit coming after the desired number of significant figures happens to be more than 5, the preceding significant figure is increased by 1. Example, 4.317 is rounded off to 4.32. Second, if the digit involved is less than 5, it is neglected and the preceding significant figure remains unchanged. Example, 4.312 is rounded off to 4.31. Third, if the digit happens to be 5, the last mentioned or preceding significant figure is increased by 1 only in case it happens to be odd. In case of even figure, the preceding digit remains unchanged Example, 4.375 is rounded off to 4.38 while 8.365 is rounded off to 8.36. Dimensional analysis. During calculations, generally there is a need to convert units from one system to other. This is called factor label method or unit factor method or dimensional analysis. For example, 5 feet and 2 inches, that is height of an Indian female, is to convert it in SI unit. 1 inch is equals to 2.54 into 10 power minus 2 meter. 1 is equals to 2.54 into 10 power minus 2 meter divided by 1 inch. Then 5 feet and 2 inch is equals to 62 inch is equal to 62 inch into 2.54 into 10 power minus 2 meter divided by 1 inch is equal to 1.58 meter. Physical classification of matter. Based on the properties, matter has been classified into 3 types, that is solid, liquid and gas. There is a table of properties of solid, liquid and gas. First property is volume. Solid has definite volume, liquid has definite volume, whereas gas has indefinite volume. Second property is shape. Solid has definite shape, liquid has indefinite shape, whereas gas also has indefinite shape. Third, intermolecular force of attraction. Solid has very high intermolecular force of attraction, liquid has moderate intermolecular force of attraction, whereas gas has negligible or very low intermolecular force of attraction. Fourth, arrangement of molecules. In solid, the arrangement of molecules is orderly arranged. In liquid, they are free to move within the volume. In gas, the arrangement of molecules is free to move everywhere. Fifth, intermolecular space. In solid, intermolecular space is very small. In liquid, it is slightly greater. In gas, it is very great. Compressibility. In solid, solids are not compressible, liquids are not compressible, gases are highly compressible. Expansion on heating. Solids expand very little on heating, liquid expand very little on heating, gas expand highly on heating. Rigidity. Solids are very rigid, liquids not rigid, known as fluid, gas not rigid and known as fluid. Fluidity. Solid can't flow, liquid can flow, gas can flow. Diffusion. The solid, they can diffuse due to kinetic energy of liquid or gases. Liquid can diffuse and rate of diffusion is very fast. Gas can diffuse and rate of diffusion is very fast. Chemical classification of matter. Matter is classified into 2 types. One is mixtures and the pure substances. Mixture is further classified into 2 types, that is homogeneous mixtures and heterogeneous mixtures. Pure substances are also classified into 2 types, that is elements and compounds. Elements. An element is the simplest form of matter that cannot be split into simpler substances or built from simpler substances by any ordinary chemical or physical method. There are 114 elements known to us, out of which 92 are naturally occurring, while the rest have been prepared artificially. Elements are further classified into metals, nonmetals and metalloids. Compounds. A compound is a pure substance made up of 2 or more elements combined in a definite proportion by mass, which could be split by suitable chemical methods. Characteristics of compound. Compounds always contain a definite proportion of the same elements by mass. The properties of compounds are totally different from the elements from which they are formed. Compounds are homogeneous. Compounds are broadly classified into inorganic and organic compounds. Inorganic compounds are those which are obtained from the non-living sources, such as minerals, for example, common salt, marble, and limestone. Organic compounds are those which occur in living sources such as plants and animals. They all contain carbon. Common organic compounds are oils, wax, fats, etc. Mixtures. A mixture is a combination of 2 or more elements or compounds in any proportion, so that the components do not lose their identity. Air is an example of a mixture. Mixtures are of 2 types, homogeneous and heterogeneous mixtures. Homogeneous mixtures have the same composition throughout the sample. The components of such mixtures cannot be seen under a powerful microscope. They are also called solutions. Examples of homogeneous mixtures are air, seawater, gasoline, brass, etc. Heterogeneous mixtures consist of two or more parts or phases which have different compositions. These mixtures have visible boundaries of separation between the different constituents and can be seen with the naked eye. Example, sand and salt, chalk powder in water, etc. Laws of chemical combinations. Law of conservation of mass given by Anton Lavoisier in 1789. It states that matter or mass can neither be created nor be destroyed. Law of definite proportions or law of constant composition. This law was proposed by Louis Proust in 1799, which states that a chemical compound always consists of the same elements combined together in the same ratio, irrespective of the method of formation or the source from where it is taken. Law of multiple proportion, proposed by Dalton in 1803. Gay-Lussac's law of gaseous volumes, given by Gay-Lussac in 1808. According to this law, when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at same temperature and pressure. Example, H2 plus Cl2 gives rise to 2HCl. One volume of H2, that is, and one volume of Cl2 gives rise to 2 volume of HCl. All reactants and products have simple ratio 1:1:2. Avogadro law in 1811, given by Avogadro. According to this law, equal volumes of gases at the same temperature and pressure should contain equal number of molecules. Dalton's atomic theory. All substances are made up of tiny indivisible particles called atoms. Atoms of the same element are identical in shape, size, mass, and other properties. Atoms of different elements are different in all respects. Atom is the smallest unit that takes part in the chemical combinations. Atoms combine with each other in simple whole number ratio to form compound atoms called molecules. Atoms cannot be created, divided, or destroyed during any chemical or physical change. Atoms and molecules. The smallest particle of an atom, which may or may not have independent existence, is called an atom, while the smallest particle of a substance, which is capable of independent existence, is called a molecule. Molecules are classified as homoatomic and heteroatomic. Homoatomic molecules are made up of the atoms of the same element, and heteroatomic molecules are made up of atoms of different element, have different atomicity, that is, number of atoms in a molecule of an element, like monoatomic, diatomic, triatomic, and polyatomic. Dalton's model, solid sphere model or bowling ball model, it is proposed by John Dalton. Atomic mass unit. One atomic mass unit is defined as a mass exactly equal to 1/12 the mass of one carbon-12 atom, and 1 AMU is equal to 1.66056 into 10 power minus 24 gram. Today, AMU has been replaced by U, which is known as unified mass. Atomic mass. Atomic mass of an element is defined as the average relative mass of an atom of an element as compared to the mass of an atom of carbon-12, taken as 12. Atomic mass is equal to mass of an atom divided by 1/12 the mass of a carbon atom. Gram atomic mass. The quantity of an element whose mass in grams is numerically equal to its atomic mass. In simple terms, atomic mass of an element expressed in grams is the gram atomic mass or gram atom. Molecular mass. Molecular mass of a substance is defined as the average relative mass of its molecule as compared to the mass of an atom of carbon-12, taken as 12. It expresses as to how many times the molecule of a substance is heavier than 1/12 the mass of an atom of carbon. For example, a molecule of carbon dioxide is 44 times heavier than 1/12 of the mass of an atom of carbon. Therefore, molecular mass of CO2 is 44 AMU. It is obtained by adding the atomic masses of all the atoms present in one molecule. Gram molecular mass. A quantity of substance whose mass in grams is numerically equal to its molecular mass is called gram molecular mass. In simple terms, molecular mass of a substance expressed in grams is called gram molecular mass. Example, the molecular mass of oxygen is equal to 32 amu, therefore gram molecular mass of oxygen is equal to 32 gram. Formula mass. Sum of atomic masses of the elements present in one formula unit of a compound. It is used for the ionic compounds. Mole concept. Mole is defined as the amount of substance which contains the same number of chemical units, that is atoms, molecules, ions or electrons, as there are atoms in exactly 12 grams of pure carbon 12. A mole represents a collection of 6.022 into 10 power 23 chemical units, that is Avogadro's number. The mass of 1 mole of a substance in grams is called its molar mass. Molar volume. Volume occupied by 1 mole of any substance is called its molar volume. It is denoted by volume meter. 1 mole of all gaseous substances at 273 Kelvin and 1 atmospheric pressure occupies a volume equal to 22.4 liter or 22,400 ml. The unit of molar volume is liter per mole or milliliter per mole. Percentage composition. The mass percent of each constituent element present in any compound is called its percentage composition. Mass percent of the element is equal to mass of the element in one molecule of the compound divided by molecular mass of the compound into 100. Empirical formula and molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound. Example, CH is the empirical formula of C6H6 is the empirical formula of benzene. The molecular formula shows that exact number of different types of atoms present in a molecule of a compound. Example, C6H6 is the molecular formula of the benzene. Relationship between empirical and molecular formula. The two formulas are related as molecular formula is equal to N into empirical formula. N is equal to molecular mass divided by empirical formula mass. Chemical equation. Shorthand representation of a chemical change in terms of symbols and formula of the substances involved in the reaction is called chemical equation. The substances that react among themselves to bring about the chemical changes are known as reactants, whereas the substances that are produced as a result of the chemical changes are known as products. Limiting reagent. The reactant which gets consumed first or limits the amount of product formed is known as limiting reagent. Volume percent is the number of units of volume of the solute per 100 units of the volume of solution. Volume percent of the solute is equal to volume of the solute divided by volume of the solution into 100. A 5% volume by volume solution of ethyl alcohol contains 5 cm cube of alcohol in 100 cm cube of the solution. Molarity of the solution is defined as the number of moles of solute dissolved per liter or decimeter cube of the solution. It is denoted by the symbol capital M. Measurements in the molarity can change with the change in temperature because solutions expand or contract accordingly, as we have learned before. Molarity of the solution is equal to number of moles of solute divided by volume of the solution in liter is equal to N by V. Molarity of the solution can also be expressed in terms of mass and molar mass. Molarity of the solution is equal to mass of the solute divided by molar mass of solute into volume of the solution in liter. In terms of weight, molarity of the substance can be expressed as molarity is equals to weight in grams divided by molar mass in grams per mole into volume in liter is equals to W by capital M into V, mole per liter. Molarity equation. To calculate the volume of a definite solution required to prepare solution of other molarity, the following equation is used. M1 V1 is equals to M2 V2. M1 is initial molarity, M2 is molarity of the new solution, V1 is initial volume, V2 is volume of new solution. Molality. Molality is defined as the number of moles of solute dissolved per 1000 gram or 1 kg of solvent. Molality is expressed as M. Molality is equal to moles of the solute by weight of solvent in gram into 1000. questions related to the above discussed synopsis. First question. An aqueous solution of 6.3 gram oxalic acid dehydrate is made up to 250 ml. The volume of 0.1 normal NaOH required to completely neutralize 10 ml of this solution is. Options are option A 40 ml, option B 20 ml, option C 10 ml, option D 4 ml. The answer is A. The solution equivalent of oxalic acid, its formula is H2C2O4.2H2O in 10 ml is equals to equivalence of NaOH is equal to 6.3 divided by 126 divided by 2 into 10 divided by 250. It is equal to 0.1 into volume in liter is equal to 0.04 liter is equal to 40 ml. Question 2. How much of NaOH is required to neutralize 1500 cm³ of 0.1 normal HCl, given that sodium is equals to its molar mass is equals to 23? Option A 40 gram, option B 4 gram, option C 6 gram, option D 60 gram. Answer is C. Solution. Normality is equals to mass in grams into 1000 divided by volume into equivalent weight. 1500 ml of 0.1 normal HCl is equal to 150 ml in normal. 1 is equals to mass in grams into 1000 divided by 150 into 40. Weight in gram is equals to 150 into 40 divided by 1000, which is equal to 6 gram. Third question. 10 decimeter cube of N2 gas and 10 decimeter cube of gas X at the same temperature contain the same number of molecules. The gas X is option A carbon monoxide, that is CO, option B carbon dioxide, that is CO2, option C hydrogen, that is H2, option D nitrogen oxide, that is NO. The answer is option A. The solution is pressure is directly proportional to the number of moles when volume and the temperature are same. N2 is equals to its molar mass into the number of molecules in it. 14 into 2 is equal to 28. CO is equals to 12 plus 16 is equals to 28. CO2 is equals to 12 plus 16 into 2 is equal to 44. H2 is equals to 1 into 2 is equals to 2. NO is equals to 14 plus 16 is equals to 28. As N2 and CO are similar, so the given option and the X molecule for us is CO. Fourth question. The volume of water to be added to 100 cm³ of 0.5 mole normal H2SO4 to get decinormal concentration is option A 100 cm³, option B 450 cm³, option C 500 cm³, option D 400 cm³. The answer is D, option D. Its solution is, as we have learned molarity equation, N1V1 is equals to normality equation, N1V1 is equals to N2V2. 0.5 into 100 is equals to 0.1 into V2. V2 is equal to 500 cm³. Therefore, water to be added to 100 cm³ solution is equals to 500 minus 100 is equals to 400 cm³. Fifth question. 250 ml of a sodium carbonate solution contains 2.65 grams of Na2CO3. If 10 ml of this solution diluted to 1 liter, what is the concentration of the resultant solution, given that molecular weight of Na2CO3 is equals to 106? Option A 0.1 molar, option B 0.001 molar, option C 0.01 molar, option D 10⁻⁴ molar. The answer is option B. Solution is molarity is equals to weight in gram into 1000 divided by molecular weight into volume in ml, as we have learnt before in the synopsis. Is equal molarity is equals to 2.65 into 1000 divided by 106 into 250 is equals to 0.1 molar. 10 ml of this solution is diluted to 100 ml. M1V1 is equals to M2V2. 10 into 0.1 is equals to 1000 into x. X is equals to 0.1 into 10 divided by 1000 is equals to 0.01 molar. Thank you. All the best for your future.